Welcome, Mission Planner. I am absolutely thrilled to have you here. Look, if you've ever stared up at the night sky and wondered exactly how we put multi-ton objects up into the heavens and actually keep them there, well, you are in exactly the right place. Consider this explainer your ultimate step-by-step tutorial for putting a satellite into space. We're going to break down the sheer science of satellite injection and the actual mechanics of achieving a stable orbit.
So let's dive right in by asking the ultimate question. Are you truly ready to place a satellite in orbit? Do you have the foundational physics locked in your brain to keep a multi-million-dollar piece of hardware from crashing straight back down to Earth? Because it's not magic, it is pure mechanics. And by the end of this briefing, you'll know exactly how the whole shebang works.
Okay, here's our mission flight plan. We'll kick things off with Phase 1, from spheres to space-time. Then move into Phase 2, the physics of falling. After that, Phase 3 covers launch and energy trade-offs, followed by Phase 4, designing your spacecraft trajectory. And we will wrap it all up with Phase 5, surviving long-term orbital hazards. Let's get to it.
Phase 1, from spheres to spacetime, understanding the theoretical foundations of gravity.
To really get orbits, we have to look back, way back. In antiquity, Hellenistic astronomers like Aristotle and Ptolemy thought the heavens were fixed to perfect, solid celestial spheres. It was a neat idea, but to make the math work, they had to keep adding these clunky, unwieldy epicycles. Then, the 16th century rolls around. Copernicus centers the sun, and astronomers actually watched comets streak right through where those solid spheres were supposed to be. That literally blew the old model wide open. By the 17th century, Johannes Kepler defined orbital paths as ellipses, and Isaac Newton handed us the math for universal gravitation. And then, finally, in 1916, Albert Einstein revolutionized everything. He explained gravity not just as some invisible pulling force, but as the actual curvature of space-time itself.
And that brings us to the ultimate gravity showdown. On one side, Newtonian mechanics views gravity as an instantaneous, invisible tether between masses. On the other side, Einstein's general relativity views gravity like a warped trampoline of spacetime, where objects are just following the curves, which we call geodesics. Now, you might be wondering, why does this matter for your mission? Well, even though Einstein's model is the most accurate reflection of reality, Newton's math is still wildly accurate for most orbital calculations today. It's just significantly easier to use. So unless we're flying a probe near a black hole, mission planners still rely heavily on good old Isaac Newton.
Phase 2, the physics of falling, mastering the orbital simulator.
To truly understand what an orbit is, we have to look at Newton's absolute genius of a thought experiment. Imagine a mountain so unimaginably high that its peak pokes right out above the Earth's friction-heavy atmosphere. Now, what happens if you fire a cannonball horizontally from the very top of that mountain, faster and faster?
What's really interesting here is what this reveals about orbital mechanics. If you fire that ball at a low speed, gravity just pulls it down in a curve and it thuds into the dirt. Fired at a higher speed, it travels much further, and because the Earth is a sphere, the ground literally starts curving away beneath it. But here is the magic trick. If you fire that cannonball with the precise, exact horizontal velocity, the ground curves away beneath the ball at the exact same rate that gravity pulls the ball down. So the ball is in continuous freefall, but it never actually hits the ground. That is exactly what an orbit is, guys. It's just falling forever and constantly missing the Earth.
Now, Johannes Kepler codified this falling motion into 3 fundamental, somewhat simplified rules. First, orbits are almost never perfect circles. They are elliptical, with the central body sitting slightly off-center at a spot called a focal point. Second, as your satellite falls closer to the planet, a point we call the periapsis, it speeds up. Then, as it flings further away to the apoapsis, it slows down. And third, there's this incredible mathematical harmony out there in space. The actual size of an orbit perfectly dictates how long it takes to complete one single revolution. Phase 3, launch and energy trade-offs. Executing the launch sequence.
You know, getting a satellite into space is actually the easy part. You just point the rocket straight up. But as we learned from Newton's cannonball, staying in space requires an immense amount of sideways velocity. So here is your actual launch sequence. First, you have a vertical launch to punch through the thickest, drag-heavy parts of the lower atmosphere as fast as possible. Then comes the absolutely crucial pitch maneuver, where the rocket gradually tilts over. Finally, for orbital injection, the rocket engine finishes firing completely parallel to the Earth's surface. And that is what generates that massive horizontal speed you need to ensure you just keep missing the ground. So, the crucial takeaway here is understanding the energy dynamic once you are actually up there. It is a constant, ongoing trade-off. Think of it like a cosmic roller coaster. You have kinetic energy, which is basically your speed. This spikes as you fall closer to the barycenter, which is just the center of mass you're orbiting. Then you have potential energy, which is all about your distance. As you coast further away from the planet, you slow down, meaning you lose kinetic energy, but you gain potential energy. And the crazy part? The sum of these two energies remains completely constant at every single point along your satellite's path.
Phase 4. Designing your spacecraft trajectory. Mapping the route for your mission.
So your trajectory is fundamentally dictated by your speed. It's all about velocity. If you have absolutely perfect balance, you get a circular trajectory. But if your speed differs even slightly from that strict requirement, while remaining below escape velocity, you end up with an elliptical trajectory. Now, if you hit the exact escape velocity, you achieve a parabolic path, breaking free forever. And if you really slam the throttle and exceed escape velocity entirely, you enter a hyperbolic trajectory, flying off into deep space.
It's super important to note here that in reality, almost all bound satellites end up in elliptical orbits. Achieving a mathematically perfect circular orbit is incredibly difficult. So most missions are going to experience that fluctuating distance, riding that kinetic and potential energy roller coaster loop we just talked about. But hey, what if your mission is to send a probe to Mars or Voyager out of the solar system entirely? Well, then you need to escape. If you hit that parabolic trajectory, you've matched the escape velocity perfectly, and your total system energy balances out to exactly zero. But a hyperbolic trajectory, that means you have positive total energy. You've got excess speed, meaning you are going to break completely free of the host planet's gravitational bonds and surge outward into the unknown.
Phase 5. Surviving long-term orbital hazards. Mitigating environmental risks in space.
Listen, getting to orbit isn't the end of the story. To maintain stable flight, you, as the mission planner, have to mitigate some serious external variables. First up is atmospheric drag. Even in low Earth orbit, there are these tiny wisps of atmosphere that steal your kinetic energy, causing your orbit to decay and circularize until eventually you burn up on re-entry. Then there's obliqueness. The Earth isn't a perfect sphere. It actually has a bulging, rotating waistline at the equator. This uneven mass distribution physically alters the gravitational field and can literally pull your satellite off course. You also have third-body perturbations, which are just the distant gravitational tugs from the sun and the moon. Oh, and don't forget the physical pressure of solar wind and radiation, pushing right against your spacecraft's hull. Space is messy.
And if you let these gravitational interactions play out over millions of years, they lead to something absolutely fascinating called tidal locking. This is a state where the constant energy exchange literally forces an object's rotation to perfectly synchronize with its orbit. This is exactly why we only ever see one side of our own moon from Earth. It is completely tidally locked to us. Okay, and remember earlier when I said Newton's math is usually enough for us? Well, there's a pretty big exception. If your mission is launching a high-precision GPS satellite, you actually have to bring Einstein back into the room. Engineers must calculate for relativistic effects like gravitational time dilation, where time literally moves differently farther away from Earth's mass. If they didn't account for Einstein's curved space-time mechanics, your phone's GPS would fail by miles in a matter of hours. No joke.
So, mission planner, you now know how to get off the ground, how to pitch over to stay in the sky, how to balance the massive energies of an elliptical orbit, and how to survive the daily hazards of spacetime. With the mechanics of the cosmos now firmly in your hands, where will your next mission take you? The next time you look up at the night sky, realize it's no longer just stars and darkness. It's a beautifully balanced equation just waiting for your trajectory.